What would happen if humanity fired every nuclear weapon it possesses at the planets of the solar system? Would Mercury crack apart? Would Venus burn brighter? Could Mars be transformed into a second Earth? And what would happen if the entire arsenal were detonated inside Jupiter, the largest planet in our cosmic neighborhood? Earth has more than 12,000 nuclear warheads. That number sounds powerful enough to threaten anything. But there is a crucial difference between destroying a world and destroying the life living on it. A nuclear weapon can erase a city in seconds. It can poison an atmosphere, devastate an ecosystem, shatter infrastructure, and alter the climate. But planets are not cities. They are enormous masses held together by gravity, and the scale of that gravity changes everything. To find out what the arsenal could really do, we have to visit each world one by one, starting with a planet where a nuclear explosion would look nothing like the familiar mushroom cloud. Mercury has almost no atmosphere. There is no thick layer of air to carry a pressure wave, no surrounding gas to form a rising column, and no wind to spread a cloud across the sky. A large 50 megaton detonation on its surface would be nearly silent. Most of the weapon's energy would leave as intense X-rays and gamma rays, striking the ground directly instead of first heating a surrounding atmosphere. The upper surface would vaporize in an instant, creating a rapidly expanding cloud of rock and metal. But the most surprising effect would not be seen above the crater. Mercury is small, yet its interior is unusually dense and rich in metal. When the explosion slammed energy into the surface, seismic vibrations would race through the planet's body. The waves could travel to the opposite side, meet one another, and continue crossing through the planet. Mercury might ring for hours. Those vibrations could destabilize distant slopes, fracture sections of crust, and send debris upward strongly enough to escape the planet entirely. The explosion would scar Mercury, disturb its interior, and throw material into space, but it would not tear the planet apart. The Moon would respond in a similar way. There is no atmosphere on the lunar surface, so there would be no ordinary blast wave and no rolling thunder. A person standing far from the detonation would not hear the explosion traveling through the vacuum. Instead, radiation would vaporize nearby lunar material, while the impact would scatter dust and soil across a broad region. The Moon would also begin to vibrate. During the Apollo era, astronauts deliberately fired mortar shells into the lunar surface as part of seismic experiments. Those controlled impacts showed how vibrations could travel through the Moon and reveal its internal structure. A nuclear blast would be vastly more violent. It could set the Moon resonating for hours and create enormous clouds of dust. And this was not entirely an abstract idea during the Cold War. In the 1950s, the United States Air Force considered detonating a hydrogen bomb on the Moon as a display of technological power. The project was eventually abandoned, leaving the Moon unscarred by a nuclear demonstration. Pluto would face a related problem, but with a more visible cloud. Like Mercury and the Moon, Pluto has no substantial atmosphere to turn a surface detonation into a familiar terrestrial explosion. High-energy radiation would dominate the first moment, and nearby ice and rock would be blasted into vapor. Pluto's surface contains abundant ice, so the expanding cloud could be larger and brighter than the one produced on Mercury. But even there, the effect would remain local. The blast could excavate terrain, scatter frozen material, and send some debris outward. It would not destroy Pluto. Venus presents the opposite extreme. Mercury, the Moon, and Pluto offer almost no air. Venus offers far too much. At its surface, the atmosphere is roughly 92 times denser than Earth's. The pressure is comparable to the pressure nearly a kilometer beneath the ocean. In those conditions, a nuclear explosion would behave less like a blast in open air and more like a detonation deep underwater. The United States tested something similar in 1955 during Operation Wigwam. A 30-kiloton weapon was detonated underwater, where the surrounding water compressed the explosion and transferred its energy violently through the dense environment. Submerged targets were destroyed or fatally damaged. Venus would impose an even more extreme version of that effect. A modern thermonuclear weapon detonated near the surface would not open a huge, lasting zone of devastation across the planet. Its dense atmosphere would compress the expanding fireball, trapping much of the energy in a small region for a short time. There would be a brief plasma burst, intense heating, and violent disturbance in the surrounding atmosphere. But compared with the size of Venus, it would be almost nothing. The planet is already hot enough to melt lead. Adding a nuclear explosion would barely change its overall temperature. Its thick cloud layers would also hide much of the flash from observers in space. The same weapon that destroys a city on Earth would struggle even to make Venus look different from a distance. Earth, of course, is the one planet where the nuclear experiment has already been conducted repeatedly. 2 atomic bombs were used in warfare at Hiroshima and Nagasaki. More than 100,000 people died as a direct result of those attacks and their immediate consequences. After that, more than 2,000 additional nuclear devices were detonated in tests. They were exploded underground, underwater, in the atmosphere, and above the atmosphere. The largest of them was the Soviet Tsar bomber, a 50-megaton weapon. Its explosion was thousands of times more powerful than the bomb used at Hiroshima. In 1962, the United States detonated a 1.4 megaton weapon in space above the Pacific during Operation Starfish Prime. The blast did not create a normal ground-level crater. Instead, it flooded the upper atmosphere with radiation and disrupted electrical power in Hawaii. Space itself became part of the battlefield. Satellites were damaged, electronics were exposed to radiation, and the near-Earth environment became dangerous for spacecraft. A comparable exchange today could destroy satellites, damage global communication and navigation systems, and make low Earth orbit hazardous for decades. The consequences for civilization would be enormous. The consequences for Earth's physical body would be much smaller. Even if every current warhead were gathered in one place, the combined explosion would not split the planet. It might carve a crater roughly 10 kilometers wide and 2 kilometers deep. Around it, the destruction would be catastrophic, with massive casualties, widespread environmental damage, and the possibility of a nuclear winter. But the continents would remain. The oceans would remain. Earth's gravity would hold the planet together. That is the pattern emerging already. Nuclear weapons are extraordinarily destructive against complex systems that depend on delicate conditions. They are far less effective against the worlds that provide those conditions. Mars is where the question becomes more complicated, because Mars has sometimes been discussed as a place humanity might deliberately reshape. One proposal involved heating the carbon dioxide ice near the Martian poles. If enough of that ice were released, the greenhouse effect could become stronger, raising temperatures and potentially making Mars more habitable. A Tsar bomber-scale detonation near one of the poles sounds like a shortcut. It would deliver enormous energy directly to the frozen carbon dioxide. But the likely chain of events points in the opposite direction. The explosion would vaporize nearby material and trigger seismic waves through the crust. Dust would be lifted into Mars's thin atmosphere. Once suspended, that dust could block sunlight, lower surface temperatures, and create a climate resembling a nuclear winter. The blast would not release enough carbon dioxide to produce the intended planetary transformation. Instead of reliably warming Mars, it could make the surface colder. The damage would not be limited to the climate. The polar ice contains ancient information about Martian conditions, including clues about the planet's past atmosphere and possible chemical evidence related to life. A nuclear blast would destroy part of that record. It could also threaten the robotic rovers operating on the surface. These machines are small compared with the planet, but Mars is one of the few worlds where human technology is already moving across the ground. A weapon meant to make Mars more Earth-like could erase some of the evidence we most want to study. Then comes Jupiter, where the difference in scale becomes almost impossible to ignore. Jupiter has no ordinary solid surface for a bomb to strike. It is a vast body of gas and fluid layers, wrapped in storms and compressed toward an intensely hot, high-pressure interior. If all 12,000 warheads were detonated in its atmosphere, the immediate result would be a temporary hot region. The energy would spread through the gas and be absorbed by Jupiter's storms. There would be no ground crater, no continent to fracture, no solid landscape to carry the damage around the planet. The arsenal could produce a violent local disturbance, but Jupiter would continue turning. To destroy Jupiter in the astrophysical sense, the weapons would have to disperse its entire mass against the planet's own gravity. That requires an energy far beyond the combined nuclear stockpile of Earth. The estimate is roughly 100 times the energy of the full arsenal, with the weapons somehow delivered to Jupiter's deepest, hottest region. And even that comparison hides the engineering problem. Getting a weapon into Jupiter is not the same as dropping it into the atmosphere. The deeper it traveled, the more extreme the pressure and heat would become. Jupiter has already endured a natural impact that dwarfed anything humanity could assemble. In 1993, comet Shoemaker-Levy 9 struck the planet in a series of impacts. The combined force was estimated at roughly 300 million atomic bombs. The collision launched atmospheric plumes thousands of kilometers high. Temperatures approached 40,000 degrees Celsius. Dark scars remained visible in Jupiter's atmosphere for months. Yet Jupiter did not ignite, it did not split apart, it did not lose its identity as a planet. A comet carrying the energy of hundreds of millions of atomic bombs could make Jupiter flash and bruise its atmosphere, but not destroy it. Saturn would respond in much the same way. A nuclear attack inside its gaseous body would create a temporary region of extreme heat. Saturn's atmosphere would absorb and spread the energy, leaving little lasting planetary change. Its rings, however, would provide something much easier to disturb. The rings are made of countless pieces of ice and rock. A blast passing through them could vaporize some of that material, excavate a temporary gap, and scatter irradiated particles outward into space or downward towards Saturn. For a short time, the rings could look visibly different, but they are not a rigid structure. They are a constantly moving collection of fragments orbiting the planet. Gravity and orbital motion would pull the surrounding material back into the disturbed region. Within days, the gap could close as the ring particles rearrange themselves. The explosion would leave a temporary interruption in a structure that is always changing anyway. Uranus introduces a stranger possibility. Deep inside the planet, pressure and temperature are high enough for unusual chemistry. Methane molecules are exposed to conditions very different from those at the surface of Earth. A nuclear detonation in those depths could send a shockwave through the methane-rich interior. The molecules might be broken apart, while the extreme pressure forced the carbon into diamond. The result could be a localized storm of radioactive diamonds. Instead of burning through an ordinary atmosphere, the explosion might help turn part of Uranus's chemistry into glittering carbon crystals falling through a world of compressed gas and fluid. There could also be flashes of light powerful enough to be detected across the solar system. But the spectacle would be far more impressive than the planetary damage. Uranus is enormous, and its atmosphere and interior would absorb the disturbance. The explosion would create an unusual local event, not a force capable of restructuring the whole planet. Neptune contains similar deep layers of compressed material, and diamond formation may already occur naturally within it. A nuclear detonation there could intensify that process, adding energy to an environment where carbon is already being forced into dense crystalline forms. The difference is that Neptune's enormous mass would make the overall effect minor. From Earth, the disturbance might be visible only through powerful telescopes. The most exotic consequence could happen deep beneath the clouds, while the planet itself continued following its orbit almost unchanged. The Sun is even more resistant to human weapons than the giant planets. Any weapon sent toward its surface would probably melt before reaching it. The heat and radiation surrounding the Sun would overwhelm the hardware long before the device could detonate where intended. But suppose one did manage to explode on the solar surface. The effect would still be negligible. The largest human nuclear weapon releases an immense amount of energy by human standards. The Sun releases vastly more energy every second as part of its normal output. A major solar flare can release energy comparable to 1 billion megaton bombs. Against that background, a nuclear blast would be less than a disturbance in a furnace that is already producing unimaginable power continuously. The Sun would not flare because of it in any meaningful planetary sense. It would not be pushed off course, dimmed, or damaged. The weapon would disappear into a star whose natural activity makes the entire human arsenal look microscopic. So, after traveling from Mercury to the Sun, the answer is becoming clear. No planet in the solar system would be destroyed by Earth's present nuclear arsenal. Some worlds would receive a crater, some would experience a seismic disturbance, some would produce unusual chemistry, clouds of dust, or temporary gaps in rings. The effects could be scientifically fascinating, and on a human scale, many would be devastating. But destroying a planet means overcoming the gravity holding billions of trillions of tons together. That is a very different challenge from destroying a city, a power grid, a satellite network, or an ecosystem. The Earth's nuclear history demonstrates the distinction. More than 2,000 detonations have already taken place, including explosions in oceans, in the atmosphere, underground, and in space. Humanity has repeatedly altered its surroundings, contaminated environments, and damaged technology far beyond the blast zone. Yet Earth remains intact. The real vulnerability of a planet is not always its rock, its metal, or its mass. It can be the thin layer where life exists, where electronics operate, and where the atmosphere maintains the conditions that make civilization possible. A nuclear exchange could destroy that layer without breaking the world beneath it. That is why the most realistic use of a nuclear explosion against a solar system object would involve something much smaller than a planet. Asteroids and comets contain far less mass. Their trajectories can threaten Earth, and their sizes make them more susceptible to human intervention. A nuclear device might be considered for deflection or disruption. Other proposed methods include laser ablation and kinetic impact. In those cases, the goal would not be to blow apart an entire world. It would be to alter the path of a smaller object before it reaches Earth, or to break it into pieces under controlled circumstances. The same weapons that are hopelessly weak against Jupiter could matter enormously when aimed at a body only a fraction of a planet's size. That may be the most important twist in the entire question. Humanity cannot seriously threaten the planets, but it may be capable of changing the fate of smaller worlds that cross our path. Nuclear weapons can scar Mercury, shake the Moon, chill Mars, distort Saturn's rings, trigger diamond-forming chemistry on Uranus and Neptune, disrupt Earth's technology, and vanish harmlessly against the Sun. They can transform environments. They can end civilizations. They can damage the evidence of ancient worlds. But against a full-sized planet, the arsenal remains a local event. So the final question is not whether humanity can destroy the solar system, it is whether we understand the difference between changing a world, changing its atmosphere, and destroying the world itself.